Hello. Lesson 2-4, the graph of y equals k times x. Now this is what you should realize is our direct variation equation. Okay? So, what happens here, the big idea of what we're trying to learn is the graph of the set of points x comma y satisfying y equals k times x, with k being the constant. Okay, we all know that that number's in front of our variable is our constant, is the line containing the origin and having the slope k. So automatically when you look at this equation, okay, you know two things. You know the slope equals k. That means you have rise over run, if you remember that from Algebra 1. And it automatically goes through the origin. The origin is 0, 0. So what you have when you're graphing this is you graph 0, 0, and then you have the slope, so you have rise over run to give you the next point. Okay? It says recall from questions in lesson 2-1 that the distance d you are from a lightning strike varies directly with time t, elapsed between seeing the lightning and hearing the thunder. The formula d equals 1/5 t describes this situation for the values given in that lesson. This direct variation function can also be represented graphically. A table and a graph for the equation d equals 1/5 times t are shown here. Now, this is what I want you to think about, and we're going to go look at that graph. But what you should automatically know, the slope is 1/5. Okay? And I know every single direct variation problem goes through 0, 0. So if I really wanted to graph this, I could graph it. I have 0, 0 as a point. I go up 1. I go to the right 5. 3, 4, 5. Get another point. I know this ain't pretty, but you should get the point here. And then you have your line. It's positive slope, so this line should be rising left to right, which obviously, as you can see, it does. So let's look at this, and they got a better graph than what Mr. Johnson does. So they put points in here. So when time is 0, distance was 0. When time was 5, distance was 1. When time was 10, distance was 2, etc., etc. T is our x in this case. D is our y. So they graphed these coordinate points. 0, 0, 5, 1, go to the right, up 5, 10, 2, to the right 10, up 2. And as you can see, here's my 0, 0 point, as we said it has to go through. And then they went up 1, to the right 5. Up 1, to the right 5. That is my slope. Rise over run was 1/5. So rise, and I'll run a 5. Rise 1, run 5. Note that the domain of this function is a set of non-negative real numbers. And the range is also the set of non-negative real numbers. When all real-world solutions to the equation d equals 1/15 are plotted in the coordinate plane, the graph is a ray starting at the origin and passing through the first quadrant. There are no points on the graph d equals 1/5 t in any other quadrants. Why is there nothing in any other quadrants? Well, in order to be in the 2 and 3, 2 up here, 3 on the bottom, that would mean we would have to have negative time. Can you have negative time? No. So therefore we can't be in 2 and 3. We're not in 4 because you can't have negative distance. Okay? So we're only graphing this section, or in this first quadrant. The reason why it's non-negative real numbers is because you could have 1, 2, 3, 4 as your time. Okay? We could have 1 second elapse. We could have 2 seconds elapse. So on and so forth. The slope of a line. Recall that the steepness of a line is measured by the number called the slope. This should be reviewed from Algebra 1. The slope of the line is the rate of change. Those two things are the same thing. You find them by doing the same thing with respect to x, and can be calculated using coordinates of 2 points on the line. As long as you have 2 points that lie on that line, you can find slope. So, if you look down here, slope equals the change in the vertical distance, okay, that's up and down, vertical distance, that's your y values, divided by the change in the horizontal distance, that's your left to right, okay? Or what they also call is the change in the dependent variable, that's your y's, divided by the change in independent variables, that's your x. So, when you have 2 points, x1, y1, and x2, y2, you put it into this formula. y2 minus y1 divided by x2 minus x of 1. Okay? And these are just coordinate points. x1, y1, x2, y2. This is the first coordinate you see to the left. This is the second coordinate you see from the left. Okay? You can pick any 2 points. And we're going to show you that in a little bit. Moving on. The definition of slope. This is what you want to have written in your notes. Okay? I realize it's review, but it doesn't hurt to have it. Okay? And they give you just a little picture. So, here's my line, and here's 2 points that lie on that line. And maybe I should use black since they're using blue. Okay? So, here's 2 points that lie on that line. They just picked any 2 points. Okay? So, they called this one x1, y1 because that was the first number that came from the left. And they called this one x2, y2 because this was the second coordinate point that they came to. Notice to find slope is rise, this is rise, y2 minus y1, okay, divided by x2, which is right here, minus x1, okay, which gives you this distance. Rise over run, okay? Example, it says determine the slope of a line with the equation d equals 1/5 t, where t is the independent variable time in seconds, and d is the dependent variable distance. So I'm going to go back to my chart, and I'm going to grab 2 points from that graph right here. So I'm going to grab 2 points, and let's just grab 2 over here. So 15, 3 and 20, 4. All right? So I'm going to go back here, 15, 3 and 20, 4. So this is my x1, this is my y1 because that's the first coordinate I see. This is my x2, this is my y2 because that's the second coordinate I see. I'm going to put it in this equation, y2 minus y1 all over x2 minus x1. y2 is 4 minus y1 is 3 divided by x2 is 20 minus x1 is 15. Well, what's 4 minus 3? 4 minus 3 is 1. 20 minus 15 is 5. So my slope is a positive 1/5. Now, we should all know where that comes out at, and that comes out in our constant of variation right there. So we should know when we look at direct variation problems, our slope is this number right in front of my variable. Okay? Quiz yourself too. What is the slope of the line through 9, 36 and 25, 100? Well, I'm going to call this x1, y1 because that's the first coordinate I see. I'm going to call this x2, y2 because that's the second coordinate I see. So, y2 is 100. Minus y1 is 36. Divided by x2 is 25. Minus x1 is, oh wow, I wrote x1. x1 is 9. Okay? Well, we should all know that 100 minus 36 is 64, correct? And 25 minus 9 is 16. So we all know 64 divided by 16 is equal to 4. So the slope of my line is 4. Well, some of you are asking, well, how would we graph that then? Well, I know there's a point. If this was a direct variation, you could go 0, 0. But this is slope 4 over 1. So I have a rise of 4 for every 1 unit to the right, which is our run. Okay? It says the slope of y equals k times x. It says observe from the example that the graph of y equals 1/5 x has a slope 1/5. This is an instance of the following theorem. Okay, this is what I was telling you about earlier. The graph of the direct variation function with the equation y equals k times x has a constant slope of k. So like I said, this is your slope, that constant of variation. To explore how the value of k affects the graph of y equals k times x, you can graph y equals k times x using several different values of k. This approach lets you view several graphs simultaneously and compares them. The graphs of y equals k times x for 4 different values of k are shown on the axis below. Okay? If you notice here, okay, all these points or all these equations of direct variation go through the origin. That's very important to know. These all go through the origin. What makes them look different is this number, our constant of variation, or what is our slope. So when there's a positive 3/4 slope, we get this line that looks like this. If I have a positive 2, that's greater than 3/4, so I have a greater slope on this blue line going up. Why? Because 2 is greater than 3/4, which is 0.75. Same thing when it's negative. Okay, these two are positive, so they went up from left to right. When they're negative slopes, they fall left to right, if you notice here. Once again, a negative 2 slope is bigger than a negative 0.75 slope. Therefore, 0.75 slope doesn't have as steep of a slope, or a decline, I guess you could say, as the slope of a negative 2. That's all I have for you today. Please enjoy. We'll see you tomorrow.